everybody. Okay, how about a more complicated example with the parallel axis theorem? So let's say we have kind of this pendulum at rest, and it's comprised of a thin rod and a solid sphere. So we like weld these things together. And then we release it from rest. It pivots about this hinge up here at the top. And we want to solve for the angular velocity over here at the bottom. Okay, how do you do this? So it's at rest. So the kinetic energy, let's say there's no friction in this hinge, so there's no work being done by friction. For the gravitational potential energy, we consider the center of mass of each of these objects, the rod and the sphere. Okay, and then energy is conserved. Right, so how much gravitational potential energy? Depends on where we pick the datum. Right, so let's say you pick the datum here. Okay, so they're both at the datum. So the gravitational potential energy for the bar and the sphere, they're both 0. And then they're both at rest. So initial 0. Okay, and then afterwards, when it's over here, the center of mass of the bar is over here. So below the datum, so the gravitational potential energy, negative. So mass of the mr for rod, okay, g L over 2. The center of mass of the ball, the solid sphere, is here. So how far below the datum is that? L plus r. So minus ms g L plus r. Okay, how about kinetic energy? So it's like the entire pendulum rotating about the hinge up here at the top. So kinetic energy would be 1/2 I omega squared, but which I? About the hinge at the top. Okay, so that's one way to do it. Another way is, same gravitational potential energy, but then for kinetic energy, let's say we can consider the bar translating like this. The center of mass is translating. And then for the sphere, the center of mass is translating like this. So there's kinetic energy for the translation of the bar. 1/2 m for the bar, v squared for the bar, plus for the center of mass of the bar, plus 1/2 mv squared for the center of mass of the solid sphere. While also the bar itself is rotating about its own center. So in other words, translation about the center of mass plus rotation. So rotation about the center of mass plus translation of that center of mass. So then we need 2 extra terms plus 1/2 I omega squared, but this is for the center of mass of the rod, plus 1/2 I omega squared, where this is the center of mass of the sphere. Okay, so all of this, or this, whichever way, we still need some information. We need, let's start here. Moment of inertia about the center of mass of that rod is right here, right from the table. This is 1/12 m L squared. Okay, for the solid sphere, right here, 2/5 mr squared. 2/5 mr squared. Okay. And then, what's the relationship between the velocity of the center of mass of that bar, the rod, and its angular velocity? What's the relationship between the velocity of the center of mass of the sphere and its angular velocity? R omega. They're different though. For the rod, it is this far, L/2. For the sphere, it is this far, L+r. Okay, so then that goes here, and then this goes there, leaving us with one unknown, omega. Okay, but how about this one? What is this? The moment of inertia about the hinge. So, in other words, we have like this bar and this sphere. What's the moment of inertia about the hinge up here? How do you do that? The moment of inertia of this entire pendulum about the hinge is over here. For the bar, it's 1/12 ml squared, but that's here. We need it to be here. So we have to add extra. How much extra? The mass of that bar times the distance between these two axes squared. Okay. Now for the sphere, here it is 2/5 mr squared. Let me double check. Yeah, right here. Okay. But then we need it to be here about the hinge, not here. So I have to add extra. How much extra? The mass of the sphere, and this distance squared, L+r squared. Okay, so all of this is this answer right here. Okay, so maybe either way, it's kind of a big mess. So try and practice both of these methods and then solve for omega, and you'll get the same answer either way. But this is good practice for conservation of energy when you have rotational kinetic energy and practicing moment of inertia. So let's do one more thing just for practice. What's the moment of inertia of this pendulum about its own center of mass? So let's say you solve for this. Here, you have an answer. The moment of inertia about the hinge. Here, about the hinge. What's the moment of inertia about the center of mass of the entire pendulum? Where is the center of mass? How do you get that? Okay, let's maybe pick a coordinate. How about like this? I'll call this x. Okay, so then in the x direction, we want the mass-weighted mean position. That's what center of mass is. Right? So where's the center of mass of the bar? Here, at L/2, times the mass of the bar. Plus, where's the center of mass of the sphere? Here. L+r times the mass of the sphere divided by the total mass. Rod, sphere. Okay, so now we know the location of the center of mass. Right, it's somewhere, let's say, say over here. So we know the location of the center of mass here. So how do we get the moment of inertia about this point over here? The moment of inertia about the center of mass. Which is more? About the hinge or about the center of mass? For sure, this is a minimum. So this is more, which means this equals this minus something. What is this something? The mass of the entire thing times the distance between these two axes squared, which in this example would be this. Okay? So always remember this concept that about the center of mass is a minimum. Right? Anywhere else, it's more. So that's why this is minus. Okay, so practice this as well. So finding the center of mass and using the parallel axis theorem. Okay, so I'll see you in the next video.